Yeah, thanks. So it will be a little bit on what I did and a lot of what others did, because it's kind of a tutorial and not my own stuff only. So I'll start with a brief description of SDN. I guess most of you know what it is to details, but for those who doesn't, or if they exist here, I'll try to give a short background. So the internet is a remarkable success, and we all know that. But I'll skip all the details. But changing the internet and adding stuff to the internet is easy only at the edges. It's easy to add applications. It's easy to change the infrastructure. But in between, it's hard to change because and we have stagnation in the protocols. It's hard to change them. Even the IPv6 is hard to be deployed. All these routing algorithms and load balancing and all this stuff that has been done in routers and switches of Cisco and Juniper and so on, very hard to change. And then the reason is closed equipment and specification and slow standardization between vendors and so on. It of course impacts performance and security and all, especially actually cost. And so the reason for that is that legacy networks are built as a set of switches that should communicate with each other somehow to make the network work. And they communicate with distributed algorithms, and they, in order to change something, you need all of them to agree on the new change of the new protocol and so on. And you need all the vendors to agree, or at least, or you need to own only equipment of one vendor in order for everything to work. And to manage that, you need human timescale to look at everything and do something with all the mess. The idea of software-defined networking is to take out this control plane from each switch and put it in some computer. And then this computer sees the entire network that it is responsible for, and it programs the switch using some API. So the switch is only data plane. It doesn't have a control plane of its own. All it has is some communication channel to this controller. Then you have this smart and slow controller. And very what is called dumb and fast switches, they are only responsible for traffic forwarding, and they forward the traffic according to whatever policy is given by the controller. So now you have a simpler management because you don't need to have these complex distributed algorithms anymore. You see everything, you can do everything. Yeah, it's very simple and so on. I won't get into the details. This is how an OpenFlow switch should look like. OpenFlow is the protocol that was proposed originally to implement SDN. So you have some hardware, flow table, and then you have software secure channel to the controller to receive this specification of the flow table. Then it puts it down to the flow table, and the packet flow only through the flow table, so they are not affected with regard to performance. So the data plane is very simple now. It's just match action tables, and that's it. And you can do many things. So you have this. You can look at this the controller as a network operating system, on top of which you can plug applications now. So here is the controller, and now the controller can give us, for example, access control, because when this phone would like to access the network, for example, it should first get an approval from the controller, let's say, and then it can then access whatever server it needs if it got the approval, and so on. You can have mobility. If the phone moves, then the controller can see that the phone has moved and then change the policies accordingly. You can have load balancing. This is a simple example. You can just load balance according to some IP address or MAC address or so. And you can have network virtualization, which is a kind of more realistic application. You can have multiple tenants living in the same network, and these multiple tenants now have different address space or a packet space, and somehow you partition the space into several different spaces. But the same switches now handle multiple tenants without affecting each other. So each tenant can only program its own address space or so on each switch, but it cannot do anything for the other tenants. But OpenFlow has many limitations, so I tried to list some of them. It has specific header fields, so if you have packets that are not packets of some known protocols, you have a problem because you cannot match based on your own protocol in OpenFlow. You have specific actions, very limited number of actions. They try to extend the number of actions supported by each protocol version, but still vendors do not comply with that, and then you have a very limited number of actions you can do on packets. And Switch remains a very basic forwarding machine, and it cannot be taken to some higher level of processing, of packet processing using OpenFlow. You need to support different target switches that provide different features and capabilities. So you program an OpenFlow controller, but then you want to deploy it, and this switch doesn't support this specific feature that you wanted to use, and this switch does support, and vice versa for other features, and so on. It's hard to program fully proactive applications. By proactive applications, I mean application that the controller sets the policies, sends it down to the data plane, and that's it, and doesn't change anything further, unless it changes something related to like some dynamic changes from some feedback it receives from the network. That's fine. But the idea in proactive applications is that user data doesn't go through the controller at all. So if I showed you before this example of the phone trying to connect, and the controller is used as an access control manager or something like that, this is reactive. That's bad. Why it's bad? Because if we have many users, the controller will be busy, and it can be subject to denial of service attacks and so on. So reactive applications are considered to be not safe and not scalable. So a good OpenFlow application would be proactive, but it is hard to program fully proactive applications in OpenFlow. And the protocol keeps changing significantly. So if you do a diff on protocol versions, you see many changes, especially in the beginning. Now it became more reasonable. Sometimes it happened without backward compatibility. So if you had a controller that speaks some protocol version, then the protocol version changed. You need to change the entire controller and everything. It was really a mess. Then came the idea of P4. P4 is an idea for implementing software-defined networking without OpenFlow, with a different protocol. And this protocol is actually, it's not only a protocol, it's also a compiler. And the idea here is that you define how the flow table looks like with regard to its structure. So you say what fields are possible and in which offsets and so on. And you kind of write a program. It looks like almost like C program that defines the how the switch behaves in general, and it's very you can do many different things that you couldn't do with OpenFlow using P4. It also has much more possible actions. It has in switch memory that you can use for some kind of hashing and so on. It has also hash actions, so you can compute hashes on the switch and so on, which you couldn't do on OpenFlow. And then when you write a P4 program, it's actually being compiled and sent down to the switches. And then on top of that, you build your controller, and the controller program the switch given this P4 specification for that switch. So it gives you much more flexibility. Yeah, so that was the background for SDN. Do you have any questions for that? Yeah.
Before compared to OpenFlow from the point of view of a central, let's say, forwarding engine, how is it related?
What do you mean?
Is P4 targeting the same idea of a central forwarding engine, for example, or a central ACL mechanism?
you could create central ACL mechanism of forwarding using P4. You just need, you write an SDN controller that speaks P4 instead of speaking OpenFlow. Now, what this controller does, it's up to you.
For example,
speaking before
Why not?
the switch speaking before the controller, you need to do a control with it. But when
So-
you're programming it,
so my question was really a remark. I think
Okay.
that it's totally different technology.
Yeah.
OpenFlow was aimed to centralize the controller to define the API or the protocol to allow for a standard central controller, while P4 is a technology that will totally work against it because it doesn't deal with the concept of a central control at all. So if you want to program P4, think about programming the forwarding plane in P4, it doesn't make any sense.
It's
Why
two
not?
different
Why not?
things.
I mean,
No,
yeah, it's totally.
P4 is a programming language.
Yeah.
OpenFlow is the most common.
Yeah,
Exactly.
it's not the same.
So
Sorry
you
if
will
it's
not, you will not decide what will be the forwarding plane assignment and code it in P4.
That's right, yeah. P4 is a language for specifying the switch behavior with regard the switch table structure and so on. But you need some protocol.
Something else.
You need some protocol to then define the behavior of that switch from some centralized controller. And for that, you need some SDN protocol, which is not OpenFlow. Okay? So, okay. So if that was not clear, yeah. So P4 is the language that defines the data plane structure, like how the table look like. And then you compile the P4 program and you send it to the switch and then it programs the data plane. On top of that, there is a control plane somewhere if you want to have an SDN switch. Yeah, if that's not an SDN switch, then okay, you just use P4 maybe. But the idea of most papers I've seen is to use it as an SDN switch, and then you need some protocol from top to speak to that switch and program the actual flow table. So you cannot use OpenFlow for that because OpenFlow is not flexible at all to do all these kind of things. So you need some kind of an augmented OpenFlow and so on. You have any question? Okay. So now I'll talk about network function virtualization. We used to have many Middleboxes in the network, and each Middlebox has some task to process packets somehow. And we have all sorts of those Middleboxes scattered around the network, and each one of them was from a different vendor with a different management API and different cost and so on. And they were kind of monolithic closed black boxes that we couldn't look inside, change something and so on. They had this high cost that you had to pay for each one of these boxes, and you cannot provision or scale the number of firewalls that you have in your organization because you need, if you want to scale, you need to buy another box. You cannot just plug something or program it to scale up. So the idea of network function virtualization was let's use commodity servers and run these applications on top of them as software. So we'll have a software firewall running in some virtual machine or container, and we may be on the same machine. We'll have a software load balancer running on the same machine, and so on. And we'll give them the separation and the isolation using virtual machines or so. And then everything will be fine because we can scale up, and we already have our own cloud. So we will have a cloud full of these machines, and we'll just scale it up and up and up and down when we don't need them, and it will work like a charm. So it reduced the cost, and it really improves the provisioning and scalability. Yeah, but there are some challenges. So first, we need to write all these network functions now as software that can be run on this NFV environment. So the current situation is that most vendors, if you ask them, it came, all this idea came from the telcos, the cellular companies and ISPs and so on. They said, oh, we have so many boxes here. We buy them for like huge amount of money, and we don't want to pay that money anymore, and we can scale and we can provision and all this stuff. So they came suggested this NFV idea, and they have all kind of consortium that defines what is NFV, which is like the biggest questions in this area now, because no one really knows exactly the answer. But then they went to all these companies that provide them all these boxes like firewalls and 5G communication gateways and all this stuff, and said, oh, now give it to us in software, because we want to run it on our cloud. So they actually gave them, many of them actually gave them software that should be doing the same things that have been done before using these boxes. But from what I heard, they have very low performance compared to the original device. Now we'll discuss why they have this low performance, but and they have limited features. So they said, okay, you want it in software? Okay, it will do only this subset of the feature that you are familiar with. It's not as good as our own box if you buy it from us, which we make much more money on, of course. There is the Open Code initiative that tries to create an open source framework and implementation, a reference implementation for NFV and for specifically for network functions that are used in telco networks. So this is an interesting initiative, and they try to provide a solution for this challenge specifically. The next challenge is to optimize the cost and performance. So yeah, we reduce the cost, and we have all this scalability fun in our network, but it might not be enough, because okay, if we want, it depends on the measurement. If you want to measure throughput, then yeah, maybe we can just scale up and up and up and have so many instances that our throughput would be good. But we'll still have the problem of latency, because if a packet before used to go through a bare metal box that operates in very high rate and very low latency, now it should go through virtual switches and hypervisors and software implementation of something that before maybe was performed in hardware. So latency is actually a real problem here. Another challenge is chaining of service functions. So when we had Middleboxes and everything was not virtual, we just plugged the middle box from one end to the input port, and from the other end to the output port or the next port in the network we would like to connect it to, and the traffic just flowed through, and there was no problem. And if we needed many middle boxes, one after each other, then we just chained them together using cables. But now when everything is virtual, we need to chain them somehow so that traffic would flow through one virtual machine and then flow through another virtual machine, maybe on another hypervisor, and so on. And this is a problem, because we need to have policies that define what chain of network functions each packet should go through. And it makes the packet forwarding much more complex in the network. So it is not easy to achieve policy chaining for a large number of policies or packets or tenants, it depends. And there also is the problem of correctness, maintaining correctness when something moves in the network, because it's virtual machines. It can migrate at any time to another hypervisor and so on. And once this migration happens, if before we had a process that is stalled for a few seconds or so, now we have packets getting lost. So that's a bigger problem. So there are many works on this area, many. It's been in the research community. It's been active for a while. I just put here one of them. Another challenge is management. So we have all these network functions spread around the network. Now they are in virtual machines somewhere, and somehow they are being scaled and provisioned and all this stuff. But we need to manage them somehow. It's not like a single box that we logged in before and just manage it. Now it might be multiple instances spread around the network, and we need to manage them. So there are efforts to make management easier given network functions from vendors. There is there are several initiatives to create management frameworks for network functions. And standardization is also it's related. So the ETSI Foundation tries to standardize a standard for NFV, for how NFV should, how a virtual network function look like and how it should communicate with the framework it runs on top. and so on. I haven't seen it converging to somewhere now yet, but it might get there at some point. So yeah, so from now on, I want to focus on security issues with regard to SDN and NFV. I'll try to highlight several papers in several areas related to that, and specifically one of my works. So I'll start with security that is provided using SDN and NFV. So we have these new technologies or ideas. Some people claim it's not new technologies, but at least new ideas. What can we do with them to improve security? The biggest area where I see the highest number of publications is DDoS prevention and detection. So this is one paper from Usenix Security 2 years ago. They use SDN and NFV in order to protect from DDoS attacks. So they use SDN to actually identify the attacks, and then they use NFV that is on the fly scaled in order to contain the attack and to mitigate it. I won't get into the details, but they start several network functions like virtual machines, and they divert all the traffic that they suspect into these machines in order to be inspected, and then traffic may be released or just dropped or logged or whatever using these virtual machines. There are also interesting works in the area of honeypots. So people use NFV in order to create honeypots on the fly, so that if traffic is suspected, they, instead of just dropping it, they send it to a network that they provision on the fly using virtual network functions that are in fact trying to track what the attacker is trying to do and to log it or to learn something about that. And they're trying to mimic the original host without affecting the original host, for example, a web server or so that the attacker would think it's still attacking the original web server, but it is actually being tracked and recorded everything, and then we can learn something about the attack other than that it happened. The same group also have a paper of that uses a very similar mechanism in order to protect from IoT attacks. So there are all these cheap manufactured security cameras spread around the world that you buy in Amazon for like $10, and you put it at home, and it's you use an app to see your child sleeping or so, but you never change the master password, or there is another master password that you don't know about. It might be also. And then you have websites in the internet that just do scanning of IP addresses and so on, and they just show you a list of cameras with geolocation and everything, so that you, if you want to see cameras in Jerusalem specifically, you can find them online, and you could just click and you see the live stream from these cameras from some people's home. So, and more than that, there was this denial of service attack that has been done using these toys, like dolls that are somehow connected to the internet. I'm not familiar with it specifically. My child is too small. But there are some dolls that have cameras, and they recorded the users, and they were connected to the internet, and somehow people used them in order to create a denial of service attack, so that these dolls initiated attacks on some specific servers. So from all around the world, some servers were attacked using these dolls, toys of children, and so on. So they tried to, and there are many works on this area, on the IoT area and the security of these devices, but they tried to contain such attacks coming from IoT devices by identifying unregular behavior of these devices. For example, if this doll should communicate with the server of the manufacturer, it shouldn't be communicating with just random servers or random IP addresses and so on. And they did that using SDN at the ISP level. So you don't need to deploy SDN at the customer home, but the ISP could use SDN in order to contain this kind of attacks. Also interesting are and related to DDoS is heavy hitter detection. So you want to detect heavy hitter flows, maybe for DDoS detection, maybe for just traffic engineering. So there are several works on that as well. This is a figure from one of these work. They extract counters from the SDN counters, and then the controller is doing the hashing and selection of heavy hitters and so on. This is another work, very interesting one from this year. They didn't have any cool figure in their paper, so I didn't put it on like this the top of the slide. But it's very interesting because they do everything only in the data plane using P4 that I just described before. So one of the strengths of P4 is that it has storage memory that you can store some state, and it also can use hash function. So you can apply some hash function on a packet. And so what they're doing, they're maintaining multiple tables on the switch and using hashing of the float on the flows on the packets, so that they find heavy hitter flows directly on the data plane without involving the control plane much. Now two industrial solutions that use SDN for security or similar goals. So microsegmentation or VMware. In VMware, they sell this product that use overlay networks. So they create overlay networks on top. You have some data center, and you install VMware software, VMware hypervisor on each server. So on each hypervisor, there is a virtual switch, virtual SDN switch, that together they create an overlay network so that tenants can create their own logical network on top of the physical network without being aware of the physical network at all. They create their switches, their firewalls, their routers, etc. They create security rules, they create policies, and so on. And everything is being compiled down to the physical network using the virtual switch on each hypervisor, so that the network itself, the actual network, the physical network, does not have to be SDN network at all. It is just whatever network you have in your data center. But the tenants see an SDN network that they're running on top of it. And they can fully program it, and specifically it has this notion of microsegmentation, that you can create microsegments and put each host in a different microsegment or multiple hosts in the same microsegment and define security rules per microsegment instead of defining like a huge firewall at the beginning at the entrance to the data center, and that's it. You have like as if you have a firewall on each host or on each microsegment. Yeah, so it gives a much better security. Also, this is a company I was an intern back then. They Big Switch Networks. They have a product that gives you monitoring fabric, they call it. So let's say you have a network and you want to monitor your network and use whatever utilities you would like to use for monitoring, maybe intrusion detection systems and so on, and loggers and anything. So what they do is they tap the network using tap ports or so, and then they connect each such tap port to actually an OpenFlow switch, physical OpenFlow switch, and then they build whatever network needed to be built here. This is your network, and these are the taps, and they built whatever network they needed to be built. It depends on the size of the network and its structure. It might be that you have multiple locations, for example. So you bring everything together to this network that is built here, and they have SDN controller here, and you define policies on top of that controller to what monitoring should be done to each kind of traffic. And then what you get is that the traffic that is collected here in the network is being steered correctly to the chain of monitoring devices that should work and monitor each kind of traffic. This is just a list of some other works. I guess I'll send a slide somewhere and you can just go and see them. So SDN and NFV gave us some new opportunities for better protection and security. It also provides some new vulnerabilities. So I'll just cover a few. This is one recent cool work that shows how an SDN controller can be used in order to bypass security mechanisms. So instead of packets, so usually packets would go from this switch to this switch, for example, through a firewall. And let's say we have a physical firewall here that in place that everything that flows from this switch to that switch go through this firewall. So they took some SDN applications and showed that in some cases you could bounce traffic from this switch using, if you know what the switch rules are, so that they go to the controller, and then from the controller they go to the other switch, and then they flow over to the destination host without going through the firewall at all. This was a nice vulnerability here. It wouldn't work much for proactive application though. It would work more for reactive applications, because reactive applications are those that take user data and send it to the controller. If a fully proactive application would not do that, and then the vulnerability doesn't exist. This is another work that showed that you can relatively easily, if you have two hosts in the network, you can relatively easily learn a lot of data on the forwarding rules between those hosts. And not only you can learn the forwarding rule, you can learn it per switch, and you can learn multiple paths by sending different types of traffic if the traffic is being forwarded differently. So they just use spoof traffic from host to host traffic. They don't know anything about the network, and they're able to learn a lot about the structure and the forwarding table content. Yes?
So how does this work? So I have two hosts external to the network?
They're in the network, like that, but you just have the hosts, okay?
So what's my mechanism for inferring information?
So they spoof addresses and so on, and they see how the packet, if it got lost, or if it, how many hops it went through, and so on. And in this, and they do it like they have for each layer, they have a completely different method to what you have to spoof, and what you can learn about it, like about the rules that use this layer. So they have for layer 2, layer 3, layer 4, and so on.
Is spoofing IP addresses a common thing to be able to do in those web?
Why not? I mean, you can just send spoofed IP address out of your computer, and
Yeah.
it will go to the switch. If the switch, does the switch verify that the IP address of each host is the same as the IP address? I don't think most switches do that. Yeah. Okay, now I'll talk about programmable security data plane, and mostly on our work called OpenBox, which is software-defined network functions. It's a joint work with Anat Bremer and David Hay, and it has appeared in SIGCOMM last year. So I said we had these Middleboxes before, and they had all these problems, and then came network function virtualization and saved us from these huge problems. And we're almost done. We just have the problem of performance and latency with NFV, but not only actually. We also have the separate management problem. So even if we had all these management platforms that I said before that are in progress for NFV, you still had to log into the management panel of each network function that is deployed in your network and define it differently according to the vendor of that network function. And there is no standard for network function management or so on. And the very crucial problem is that each one of them has a separate control plane. And this also gives you other problem. Another problem is that you have very limited functionality and limited innovation. If you want to change something, you can't, because you are tied to the API given by the vendor of each function. But if you look into these black boxes, and you think how they actually work, they actually do pretty similar things, most of them. And not only they do pretty similar things, they are modular. They even use the same module sometimes, but they do it different, like separately. Each one of them run the same module, but separately from the other. So we may have some opportunity to leverage leverage this fact to improve performance. So this was our starting point, and we created this software-defined framework for network functions. And our idea was to decouple, as SDN did for forwarding devices. We wanted to decouple the control plane of network functions from their data plane, so that we have a control plane on top of everything, and data plane is like dumb and fast, as I said in the SDN context. So instead of having network functions deployed everywhere in the network, we now have network functions deployed on top of this control plane. And what we have in the network is some kind of device, which can be software or hardware, that actually realize the logic given by this controller. And the benefits we get are easier and unified control, because we have one point to control everything in the network with regard not only to forwarding, but also to network functions and packet processing in general. We get better performance and improved latency, I'll show you soon. And we get scalability and flexibility that we didn't have before, isolation between tenants, and some room for innovation, because now it is much easier to extend the functionalities of all this data plane, let's say. So if before in software-defined networking, if now we have a high cost of Middlebox and limited provisioning, scalability, and management, we had all these problems before with switches, and there the solution was to use SDN. So why not here as well? Okay, so that was the solution before for the forwarding plane. And we know that about 50% of the appliances in networks are not switching devices. They're these more complex devices. So we need to handle them as well. This is how the framework looks like. We have this Northbound API for defining network functions. Now network functions are defined on top of this controller instead of as just being deployed everywhere in the network. We have this controller that is responsible to unify multiple network functions and send the directives to the data plane using a protocol we defined. And this is the data plane. This is where packet flows. Packet do not flow through the controller also. They just flow through the data plane. And the data plane realizes the logic given by the controller. Additionally, we get isolation between the tenants. If we have multiple tenants, we have support for hardware accelerators, and you can dynamically extend the protocol. So the idea here is also called in literature network function decomposition. So we have a network function, but let's look inside. So inside we have, we can describe a network function as a graph, usually directed a cyclic graph of operations. So for example, a firewall would read a packet, classify it based on the header, and then decide to either drop it or send it out without dropping it, or raising an alert, or so on. And a load balancer, which is completely different, like logically completely different, would do very similar steps. It would read packets, classify based on the header, then it would either output the packets or send them, or modify them and then output the modified packet. And there are more complex systems, like intrusion prevention system would read packet, classify based on the header, then do depacket inspection, and it might have multiple depacket inspection engines, depending on the packet type, and then it will send alert or not, and so on. So this Northbound API is actually an API to describe these graphs. Each graph is like the graph structure, and for each block there is some configuration. And then given these graphs, the controller then unifies them, and I'll talk about it later soon. But it is also in addition to graphs, you can also request to receive information about events. So you register for events in the network, and then you get notifications on events, and you can request load information from the data plane through the controller, and then you get it back as well. So now you can have multiple tenants run multiple applications for multiple policies in the same network. And you have, by design of this Northbound API, you have isolation between the applications and the tenants because each application is defined declaratively. So it cannot query anything about other applications. If you can connect this controller to an SDN controller, and then you have network-wide view, and then you can control also scaling and provisioning and so on in the data plane. So one problem we had was, okay, we have two network functions, and we want to run them on the same physical device in the data plane now, and we know something about what these network functions are doing. Can we do it better than just concatenating the two graphs? So we could just concatenate the graphs. So this is the firewall part, and this is the IPS part. We're just not outputting and input back the packets, but more than other than that, we don't do anything, because the performance of this graph would be roughly the diameter of the graph, and more precisely, it would be the number of classifiers in the diameter, because classifiers are usually the most time-consuming part of a network function. And then, can we shorten this diameter? So, in the paper, we have an algorithm that actually shortens this diameter. It's a very greedy, simple algorithm that looks for similar classifiers and just merge them together. As you can see, it increased the number of the total number of blocks, but this doesn't have any real effect on the performance, because the performance is only defined and only affected by the diameter of the graph, the number of blocks a packet goes through. So what kind of blocks we may have? We may have many different blocks. We may have blocks for classification, for compression and decompression, modification, normalization, and many more. We try to define a very long list of these, but we know that it's not the end. So we have a reference implementation for a service instance that is deployed in the data plane, and it realizes the logic of network functions given by the controller. Now, this instance is speaking with the controller using the protocol we defined, and another instance can be built, for example, in hardware. As long as it speaks the same language, the same protocol, it should be fine. Not only that, I don't have a slide for that here, but the new instance that you would like to create in hardware, for example, doesn't have to actually implement everything we define in the protocol. It just needs to implement only the very basic stuff. And then it can forward the packet for further processing on a different instance, for example, our software instance. So I won't get into that into details now, but yeah, okay. For performance improvement now, only the fact that we have multiple network functions running on the same physical instance gives us performance improvement. And let's consider this service chain. So we have if packets go from host A to B, they have to go through a firewall and then through an intrusion prevention system. If we just send them through this chain, and each one of them was, let's say, a virtual machine, like a network function, a virtual network function, then we'll get this performance. The firewall would have superior throughput over the IPS because it's much simpler and it doesn't do all this deep packet inspection stuff. And the latency of firewall would be lower. Now, ignore that for a second. If we measure the entire chain, then the throughput would be dominated by the firewall. It would be by the IPS. It would be the throughput of the IPS. It's the bottleneck. And the latency would be the sum of both. OK? So it's somewhere here. Now, with OpenBox, so this point moved. It should be the sum of both. With OpenBox, we use the same two virtual machines, but we deploy our service instance now instead of these standalone network functions. And we then load balance the traffic through these two instances. So we now have two running instances running the same logic. So we get the throughput is actually double the throughut of each one of this machine. So it almost has twice as the throughput here, but not exactly. And the latency is the latency of going through a single virtual machine, and that only performs a slightly bigger graph, but still a single virtual machine.
The performance numbers are startling. Like a firewall that does 500 megabits is really slow.
This is a software implementation of a single core firewall with many rules, but on top of everything, I skipped the implementation part, but everything is implemented on a click. And if you implement a very simple firewall on click, that's what you will get on this computer we ran.
So what are you using in terms of getting the packets from the NIC? What click is it?
Oh, it's click without DPDK and without any kernel bypass and so on. But if you have that, you have that everywhere. So yeah, we weren't able to use DPDK on the specific computer we had for that. But well, if you have DPDK, you have DPDK here as well. So I think it's still apples to apples comparison.
Well, it's not clear, right? Because when you multiply these by, I don't know, 1 or 2 orders of magnitude, all of a sudden you start seeing different things, right? Completely different. For instance, on a single core with normal processing, you should be able to do easily 14 million packets per second, minimum size packets, right? On a single box, for instance, we could load balance 40 gigabits of traffic, which is like 2 orders of magnitude more.
I think it really depends on the rule set that you have and the number of rules in the firewall and the size of tables and so on.
That's true, but basically when you have such low numbers, it's not clear what you're measuring, and any performance measurement is more or less irrelevant. When it's so low, it doesn't say anything.
Well, you're the first to say that. I don't know. I think that it's consistent. It's not that like we get different numbers every run or so. So I think
no, it's fine. But the thing is, when you have, I don't think you're measuring the right bottlenecks. It could be that the system you have is completely inefficient when you go faster speeds, and you get, with and without are the same. Right? So that's why I mean, network speeds are 10 gigabit. They used to be 10 gigabits. Now it's 40 gigabits and 100. So when you show something that's not even a gigabit, then
well,
something there's a big question.
Okay, I'm sorry, but I tend to disagree about the question mark here. I mean, if it was a production system, then we could argue that we get to 10 gig or not getting to 10 gig and so on, but we just compare like one implementation running this way or this way, and that's it. So I don't think it makes that much of it's not that important to use to optimize this implementation to use all the whatever kernel bypass and stuff we could use in order to get to the number that we are used to see in specific like in production environments and so on. But okay, I agree that it would be better to compare it on like 10G network and so on. So yeah, anyway, on these measurements, we see 86% improvement in throughput and 35% improvement in latency. You're welcome to play with our code. It's available. And this is some other list worth mentioning on similar work, similar areas. Not exactly the same goals, but similar. Now, the rest of things I want to show is on verification, just a little bit. I know there is a talk on verification later, so I won't get into much details, just a few new papers on this area using SDN. So this is a new paper that tries to verify remote procedure calls between microservices in let's say Amazon, for example. I think they used Amazon specifically, and they do that using virtual switches that they program using some SDN protocol that they define for this some SDN rules they define for this work, and they were able to have some kind of initial verification of remote procedural calls between multiple microservices that compose together an application, for example. So many applications now are programmed as a set of microservices chained together in some way through remote procedure calls. And they propose this vSwitch usage for enforcement of remote procedure call validity between such microservices. There were many works on verification of the design of SDN applications. So you write an SDN application. Now everyone can write an SDN application. You don't need to be Cisco to control your network. But now you want to verify that it works. So you may want to verify connectivity. You may want to verify that the rules are actually enforced as you define them and not in different way. And you may want to see that there are no bugs, because bugs is a security problem at the end. So this is a new, actually there are two new papers very interesting on this area. This is one of them. They create a kind of a static verifier. So you do not program directly your SDN controller. You give some kind of specification for your application, what they should do, how they should do that. Then it is being verified. Then they have some kind of a compiler that provides both OpenFlow and P4 specification to the SDN controller. The SDN controller runs the OpenFlow, communicates the OpenFlow definitions to the switches. If it uses P4, they also use the P4 compiler to program the switches before, and so on. So it's nice work in this area. There is work on verifying complex reachability. Specifically, it's on reachability in a network that has network functions that change packets while they're moving in the network. So there are many papers on reachability without changing packets. It's kind of easy, let's say. Not that I did that. It's not easy for me. But then they said, OK, but in most networks, packets change during their flow in the network, and then it's a real problem, and all these solutions do not hold. So they give like a good starting point for a solution, a large-scale solution. And one of the big problems they had was how to scale it to bigger networks. Because it's not a simple solution, scaling it to a large network was not like trivial, just scale everything and that's it, because the data structures and so on were very big. So they use a notion of slicing to reduce the problem size, and they slice the network to only the switches and entities that are correspond to a specific, let's say, a specific policy. They would try to check that it works or not, and so on. And instead of checking the entire network from the entire set of policy, they check each slice for each policy, and they verify it this way. And they needed to have some abstraction for Middlebox behavior to define what is the change that being done in each Middlebox, in each network function on packets, to understand that what happens in the network. So this is what you have to supply the system in order to understand how the network behaves. Yeah, so that's all I have. Any questions? Okay, thanks.